You know, science is a bit like detective work. At some point, you've got to show some proof that what you're saying is true. Take plate tectonics, for instance. We've become pretty good at using this idea to explain how Earth's giant puzzle pieces create things like mountains. But there's a catch. It's tricky to test if we're on the right track because this puzzle solving happens really, really slowly. But wait, a study in the Italian Calabrian mountains found some of that evidence stuff. Surprise, surprise. It might just shake up our whole understanding of mountain making. Now let's dive a bit deeper. Plate tectonics is like a secret force, invisible but powerful. Deep below the Earth's surface, the mantle acts like a pot of simmering soup, with warm currents rising up and then cooling and sinking back down. Up on the surface, the Earth's crust, those big solid puzzle pieces, are like toys floating in a pool. Not your everyday pool, I hope, but you get the idea. When these plates bump into each other or pull apart, they create stunning landscapes like valleys, volcanoes, and mountains. We often think that mountains pop up when plates collide. Imagine a mountain range forming as one plate slides under another. It's like the top layers of rocks get scraped off and pile up, kind of like clearing frost from your windshield. All that piled up rock makes the mountain like an iceberg made of stone, floating on the molten mantle below. So it makes sense. The faster plates collide and create more rock, the quicker the mountain should grow. But here's the hitch. Most plates move at about the same speed as your fingernails grow, and mountains take millions of years to build. So, testing our ideas is a bit like trying to time mountain growth with a stopwatch. Nearly impossible. But here's the exciting part. In June 2023, a group of clever scientists published a paper in Nature Geoscience that shook up our understanding of mountain building. They came up with a cool new way to figure out how fast mountains have been growing over time, all by studying the lay of the land. Picture this. They zoomed in on the toe of southern Italy, where the Calabrian mountains have taken shape as the African plate crashed into the Eurasian plate. The scientists, hailing from the U.S., played detective by combining various geological tricks. They checked the age of rocks by looking at special elements inside them. Then, they looked at the shapes and features of these mountain rocks to figure out when and how they formed. This helped them piece together the speed of the action, how quickly the land was going up. Imagine it like this. Flatter parts of the mountain landscape happened when things moved at a snail's pace. But those steeper sections, well, they suggest things got moving really fast. And if you spot rivers slicing through the rocks, that's like a time capsule telling you when the land shot up. Here's the big twist. They discovered that the Calabrian mountain building wasn't a smooth, constant process. It was more like a stop-and-go journey. Even stranger, the speed of the mountains didn't match the speed of the African plate's subduction, the one sliding under Eurasia. When the subduction was fast, the mountain growth was slow, and when the subduction slowed down, the mountains shot up. This totally goes against what we thought about how mountains form. It's like breaking all the rules. So, these scientists had to come up with a new idea. Remember those convection currents deep in the Earth's mantle? They think the part of the African plate that dove under Eurasia messes with these currents. And this, in a weird way, affects how high the land gets. It's like saying mountain building is more than just skin deep. There's a whole hidden story beneath. It's like solving a super cool mystery. Now let's dive into something super fascinating called dynamic topography. This is like a secret we've heard about but never actually seen in nature. Here's how it all plays out. As the African plate heads downward, it pulls some of the mantle along with it. This downward motion sparks a brand new kind of current deep within the Earth's mantle. Imagine the mantle material flowing down near the subducting plate, heating up and then coming back up to the surface a bit farther away. But here's the cool part. This strong downward flow near the subduction area kind of sucks the crust down in that region. It's like a tug of war, and it cancels out any upward movement caused by the crust thickening. So, while the subduction happens quickly, the uplift is slow. But here's the twist. This doesn't last forever. Sooner or later, that slab of crust hits a special area in the mantle about 660 kilometers deep. Below this point, the lower mantle is super dense, and the piece of swallowed crust just rests on top of it. Subduction slows down, and eventually the slab breaks apart and falls away. This disrupts the strong current and downward flow. Without the tug from the mantle and the weight of the slab, the crust bounces back up. Suddenly, the uplift becomes fast, even though the subduction and crust thickening have slowed down. The main idea is still the same, but it turns out there's a whole lot more to the story of plate tectonics. The crustal plates aren't just passengers floating on the mantle's wild ride. They can actually change what's happening deep below. And this, in turn, affects when and how the surface features form. But here's the fun part. We're not done yet. We need to find out if this process happens in other places too, not just these mountains. The scientists hope that their new way of looking at things will help us understand how mountains form all around the world. This study shows us that our Earth is like a big, complex puzzle, where even the rocky puzzle pieces can change the game underwater. And when we figure out how and why mountains grow, it helps us piece together the history of our planet and, well, the history of everything on it. Cool, right? Like and subscribe to our channel for more interesting videos like this one. Thank you for watching.